Good afternoon. I guess this is about the last session, so I'm just going to go for it here. Welcome to this session on using Apache Solr for images as big data, a case study. My name's Kerry Koitzsch, and I work for a company called Wipro Technologies, LLC. Our company recently has been doing several very interesting big data initiatives, and in particular, we're doing an initiative on what we like to call images as big data, which is something we've kind of been trying to question and define in our own minds. And in this talk, we'd like to share with you some of the architectural process we went through while we were evolving the Images Big Data Toolkit, which is a modular distributed analytics system. It's specifically designed to perform operations on a variety of images, signals, and other sensor data, various kinds of radar, distance detecting sensors, and other information, sometimes with sensor fusion and other interesting things. The images big data approach, it was based on the realization that images are just another kind of big data, and they share many of the attributes that non-image big data has. The volume may be modest. I mean, you may not be getting as many images coming in as you might do, say, log entries or single lines in a log file or something like that. But the other attributes, velocity, variety, veracity, the big 4 V's of big data, they're all there as well. So with that realization, we wanted to focus in on images as big data and evolve a toolkit using standard components and see what happened. So with that, let's go on for the overview, and we'll turn to the first thing, which was trying to set our initial objectives when developing this toolkit, Images as Big Data Toolkit. And the first thing we realized is we had aspirations. We aspired to doing a few things. One of the things was we wanted to support some of the old school analytics and old school analytic visualizations. And what that means is the old bar chart, histogram, scatter plot kinds of approaches. But we also wanted to modernize the technology and use new concepts of visualization as necessary and things we thought were interesting. Here I've just kind of made a laundry list of some of the things that we're going to show later in the presentation. I made a special note to myself to mention glueware. We discovered that that was extremely important when building this kind of system. We're trying to be as modular as possible. We're using Lucene Solr as the basis of our search engine, but we have a few people in the minority who want to swap in an Elasticsearch module. So we allow them to do this. We allow Solr and Elasticsearch to live in harmony within our toolkit. And we try to keep the peace that way. In the course of doing our testing and our evolution of this toolkit, we essentially took two scenarios with a very similar use case. One of them was to visualize crime statistics using geolocation and other data. Another one was an automated microscopy example in which we automatically analyze microscope slides. So these two kind of test applications came out of our vision, if you will, of our original use case, intelligent search, modular components, several other things we agreed upon in the design. So with that in mind, we went on and we kind of correlated and listed all the display types we wanted to have. We want to aspire to notebook-based visualization because it's the best combination of having a read eval print loop and an interpreted kind of approach to problems. Plus you have a computation engine and you have your visualization component as well. On top of this, you can add your search technology module. So we wanted to have this kind of wish list of capabilities. We want to do images with overlays, show the results of our searches and so forth, kind of standard technologies to use. We wanted to be able to customize data visualizers. We wanted to leverage the Lucene Solr capabilities to make our own custom searches on different domain areas. So these were a few of our goals when we started out. Old school statistical visualization, this was a must for us because we're not necessarily working with software people, we're working with physicians, we're working with technical people who are operating microscopes, and they're not necessarily in the same space as far as requirements and what they need to do. So one of the ways we had a common language was to look at old style statistical displays. And here are a few examples of what we came up with. You know, they look very familiar, I'm sure, to all of you. I'm just going to flip through them rapidly under the header of the old school visualizations. Now, as we all know, physicians, people that work in doctors' offices, people that work with this automated microscope technology, they tend to be relatively conservative in their technology choices. So seeing a bar graph makes them feel good, and we kind of stuck with that to a certain extent. We stuck with, even if we're using our advanced classifiers, we're still sticking to standard displays like this. We're using standard time series. We use OpenTSDB for our time series data in the background, but we still use the standard displays. We use Hive, Hadoop, we use Apache Spark, we use Flink technologies on our distributed backend. But in the visualization, the top level that people see, we're still using tables, we're still using JavaScript. We're tending to be very old school in the UI and the front end. Sometimes we don't even have web interfaces. We just have workstation interfaces. If we really want to be retrograde, we do that. But now we start to progress a little bit and evolve. This is more in our back end. We started thinking about our data sources. We want to use graph databases. We want to use Neo4j. We want to be able to import CSV data, especially for things like the crime data example that we've been working with. This tends to be large batch files that come from the police departments. They're in various CSV formats, which, as you can imagine, makes a Lucene Solr very flexible as far as the schema goes. We usually get some kind of latitude, longitude, or time point data with it, timestamps. And it all fits in with Lucene and Solr very readily. Here's just a quick example here of some of the CSV data and the crime data. We can throw the crime data at the Neo4j interface once we're done working with it. We can either use the query language with the graph database, or we can use Solr. We can also adjust the display to suit. These happen to be just individual floating nodes of the crimes around Sacramento. And you can see some of the properties of these at the bottom of the display. We have some other things that we're experimenting with. These also tend to be pretty retrograde visualization things, using JavaScript, using Go.js. We're using AngularJS now for our front end. Here's just a little bit more. I tend to fixate on notebook-based visualization, so forgive me that there are a few of these extra slides in here for that. Moving on to the real technologies involved in our examples. We are doing a distributed system, and we originally stuck with Hadoop. We're also using Spark and some of the other things like Flink now. We use HBase, we use HDFS as the file system. We use a combination of Lucene, Solr, and Cassandra for our data storage. We use a Solr-based what we call intelligent search. We also have a component living in harmony with all this, which is based on Elasticsearch, Logstash, Kibana visualization. We use Kafka for messaging. So these are all, as you can readily see, they're all standard components, third-party components. Each one is a module in our toolkit. We use Zeppelin or Jupyter as our notebook technologies. And here's a quick example of a Zeppelin data set being visualized on the map here. Solr, Zeppelin, Cassandra together. A few conclusions from all this geolocation visualization. We found that we could readily import crime data over several years or over months or over smaller time intervals into Solr very readily. We can do an ETL process on these and push them back into Solr or into Cassandra or into our Elasticsearch module for that matter very readily. We can also use different visualization tools on top of this. And we can use Logstash or Flume or any of the importing tools very conveniently and in a very plastic kind of way when we're evolving this toolkit. Apache Tika is very useful as a support library which converts document formats to a universal form, if you will. Here we finally get to a Solr slide. Once we import the crime data, we essentially see records like this, and this is just an example of one. Different police departments use different structures. They use different geo units. They don't always use lat long. They don't always have lat long in the same order. They don't always have the same time intervals. So there's a lot of things to accommodate as far as this kind of data goes. We had to have several discussions when thrashing out this use case, what all the data massage and validation and data cleansing really would mean with Solr data. These are coming in as unwashed CSV files, and there's no validation done. So there can be anything from misspellings to missing fields to strange characters, you name it. So our data cleansing phase in this is quite aggressive, you might say. Here's a similar thing just to show a contrast, same crime data in JSON format for Kibana, working along with Elasticsearch. One of the great things we found we could do is work with the data in Solr, import it over to the ELK stack module, and then we could see visualization like this, where the larger red dots are basically the high crime neighborhoods. So over the course of years, you can see this evolve and for different cities. And you can correlate other information to why this is happening and why these happen to be where they are. The larger red dots are extremely high crime areas. One of the interesting things that came out of this investigation, we kind of did this for fun because crime data is dramatic and all that, and we needed some excitement. But one of the things that was fallout from this experiment was we could start to correlate other causal factors into our model. And we discovered that even for different cities, even for different time periods, most of the high crime areas are related to gang activity in a nutshell. So there's a high correlation between the two. A lot of times it's a conflict over territory, basically. And you can really see this when it's a city like East Palo Alto, which has a lot of this kind of activity. So useful conclusions can be drawn from looking at these visualizations and having domain experts come in and say, oh, that's because there's gang X is there. We found that to be kind of interesting and kind of a validation of our approach in a sense. Images, big data visualization. Instead of this CSV data coming in this instance, we have images coming as the data source. One of the first things we do is throw a lot of the information away depending on the kind of problem we're trying to solve. Sometimes we even throw all the color information away if the boundaries of objects is enough, and not just for storage space reasons, but also for complexity and computation reasons. So what we do is we perform a feature extraction phase, and then we can throw this simplified data, the image features, at things like a deep learning algorithm or a machine learning algorithm or a statistical algorithm. So when we were looking around and looking for inspiration for how to do this in an organized way, we essentially did software archaeology. We went back and looked at the early MIT work, and we really looked at something which is called the MIT Vision Machine, which was a very early architecture. They didn't actually implement this because of essentially the technology restrictions, but they conceived it very, very interestingly. And we had the ambition of trying to implement at least part of this. And if you look at this, it's essentially a data flow. You could readily imagine it operating under Hadoop or under Apache Spark very readily, where all these things are running in parallel. You're grabbing out, you're deconstructing the image, finding edges, finding textures, looking at color if you need to. If it's video, you're looking at motion. Sometimes you're looking at stereo pairs and getting three-dimensional information. We were really inspired by this diagram that Paggio's work and Paggio's team came up with. And we had the ambition of trying to actually implement this using modern Hadoop-esque technologies. And this is part of the inspiration for the Images Big Data Toolkit. Our architecture was relatively simple, and here it is. Data sources, you might imagine this coming in from Apache Kafka or a system like that. Image processing and analysis, and again, you might imagine something like Deep Learning 4J or some of the other toolkits like Mahout, H2O, some of these other machine learning toolkits. Intermediate result repository, we've used a variety of NoSQL databases there. And finally, we end up with results, extracted features that are labeled as to this is a corner of a house. This might be a road or some other labeled feature. The very last block here is where it gets interesting as far as Lucene Solr goes. We wanted to have our Lucene Solr intelligent search module and dashboards at the end of it, questioning our results that we got from our image analysis. And one of the examples of this system is one we built here, where you can actually see the linear features being drug out. We pipe these into Cassandra database, and then we're able to search these linear features by a number of attributes associated with them with a Solr-based intelligence search. So you can see in white here a lot of these things are pulling out line segments. You can see a little bit how it's pulling out cars, some of these other things. Straight lines don't really exist in nature, so if you find a straight line, you've pretty much found a building or some other man-made object. So we're very interested in things like that. We've done a number of prototypes using this same architecture diagram that you saw before, this one, trying to emphasize different parts of the process. One of these things that we had initially tried to do was we have a client, they're very interested in automated microscopy. They want to take a cartridge of microscope slides and squirt the slides through the microscope, and it's a regular optical microscope like you had in high school biology or something. Use an electronic camera, analyze the images. So we came up with this diagram specifically to get feedback from them about it. We have some of the technology components around the edge, database component down below. Cassandra result database down here. What's noticeably missing from this slide of Koitzsch is where's the search, right? Where's the Solr? Well, at that stage of the game, we were still pondering what our search strategy was going to be, so it's not in this diagram. Here's an example of another kind of data people are interested in. It's from an electron microscope rather than an optical one. This is the original image. We do a feature extraction. We can find ellipses and find rough boundaries of objects we find on the slide. We don't have to stop there. We can find contours. We can find lines, as you saw in that earlier example. So as far as pulling features out of the data and putting them within our Solr data, it's relatively straightforward and very flexible. Here's a picture, just in case you were curious, the kind of optical arrangement we have. Electronic camera. We have a cartridge-loaded slide dispenser, which puts the slides through. And here's the control software. Pretty much data ingestion from what the electronic USB camera picks up. In this case, we're putting it into a Hadoop HDFS database, mostly metadata in this case, but here's one of the things that we do get out of the result, and this is Solr again. The metadata for these kinds of applications is almost as important as the data itself, because you have a lot of information about the microscope settings, what kind of staining was used, a large variety of other factors, resolution. You might have other research results that are tied to this that the physician is interested in or working on. So you have citations. The metadata is very complicated, but we found, starting with a very simple schema in Solr, we could evolve it and we could get new requirements from the physician. And he might say, I want to see what the lighting on this slide is. How intense is the lighting? What setting is it? Is it polarized? Lots of other details. And we can say, sure, we'll change our schema, give us the data, we'll send us a CSV file or hook us up to a stream. We can put it right into Solr with very little disruption. And we can also evolve our other schemas that might go along with this in parallel. For example, we might have relational schemas for this data in Oracle. We might have, perhaps we might have schemas in Cassandra. So this enables us to kind of keep them consistent and organized. Here's another prototype we did with optical microscope. Simple overlay showing one anomaly in the top cell. And when we were using Solr and Cassandra and all the other databases and data like this, we immediately noticed how useful the top-in function of our queries was. If you have 500 cells on your slide that are showing like this, there's a large number of them, and you're deconstructing those cells looking for anomalies, you don't want to show the top 10,000 results. Maybe you just want to show the typical first one. So in this case, that's what we're doing. And you can see that in the upper left-hand corner labeled there. It's top N1 or top 1 result. So again, this is something Solr is good for, is to limit results and characterize them in the query very accurately. Here's another view of the data pipeline. In some cases, we have, for example, we work with drone photography in which there are 2 cameras on the drone with a mind towards grabbing out stereo pairs and estimating distance. Drones are a very interesting problem because there's a strict weight requirement. You can't have too heavy a camera, and once you have 2 cameras, it starts to be problematic. So we try to think of all kinds of ways to cheat to get our distance information. One of them is flying the drone up one side of a landmark and back again on the other side and pretending they're left and right and collating the images. So until cameras get lighter and we get down under 2 kilograms or so, We want to do some of this sensor fusion, which might be anything from actually combining image data to just simple collation. Oh, this left one goes with this right one, and maintaining the correct sequence. So we looked at things like sensor fusion a lot. We looked at a lot of pre-processing in the sensor, which we call smart sensors or intelligent sensors. All of this is using Solr as the back-end search technology. So it's a vital component of all our prototypes now. We tend to do Elasticsearch as kind of an afterthought or to placate some Elasticsearch diehards. But all things considered, we're very keen on continuing to use Lucene and Solr as our search technology and continue to kind of question and redefine what intelligent search means to us and our clients. And I'm at the conclusions and future work slide now. Conclusions, I think as technologists, we kind of lose track of the fact that although Solr and Lucene are extremely powerful in the technology they provide, sometimes we lose track of the fact that that Solr and Lucene technology, they have a strategic value, they have an organizational value, they have a mediating value, because they play well with other components. You can integrate one of these technology stacks. You don't have to worry about Solr fitting with the other components. You can use Spring Framework and Spring Data. You can use Spring Data for Solr as glueware. You can integrate all these things very readily, and it makes your technology stack choices so much more easy with a reliable search component. If you're developing custom searches, you can continue to evolve it without too much disruption, just because the Solr underlying mediating, supporting infrastructure technology is there. So that's why we like it. We like Solandra. We like the components that fit between Cassandra and Solr, say, and many of the other ones which exist, and we try to leverage those as much as possible in our prototypes. We found that considering what Solr can do for us is very much a part of our strategic approach to doing these prototypes and supporting our clients. And you know, on this slide, of course, I have a laundry list of some of the things we're going to try next. But basically, it's more of the same, perhaps in different domain areas and perhaps with more challenging data sets and complexity. I think that's about all I have, in case anybody has any questions. Thank you.